Amplifier classes categorize electronic amplifiers based on their conduction angle, the portion of the input signal cycle during which the amplifying device, like a transistor or vacuum tube, is actively conducting current. The class you choose fundamentally dictates the trade-off between linearity, that is, how accurately the output mirrors the input, and efficiency, how effectively it converts DC power into useful AC output rather than wasting it as heat. The analog classes. These traditional classes operate by amplifying the continuous analog waveform. Class A. In a Class A amplifier, the transistor is biased so that it remains constantly on and conducts current through the entire 360 degrees of the input waveform. Advantage: exceptional linearity and extremely low distortion because the transistor never switches off. Disadvantage: terrible efficiency, typically 15 to 25% in practical circuits. Because current flows constantly, even when there is no input signal, the device generates a massive amount of heat. Class B. To improve efficiency, a Class B amplifier uses two transistors in a push-pull arrangement. Each transistor only conducts for exactly half of the waveform, 180 degrees. One handles the positive half, the other the negative half. Advantage: much higher theoretical efficiency up to 78.5%. It wastes no power when there is no input signal. Disadvantage: it introduces crossover distortion. Because transistors require a small threshold voltage, like 0.7 volts for silicon, to turn on, there is a brief dead zone where neither transistor is conducting as the signal crosses zero. Class AB is the industry standard compromise for most high-fidelity analog applications. It operates like a Class B push-pull amplifier, but both transistors are biased to conduct just a little bit more than 180 degrees, usually around 190 to 200 degrees. Advantage: by keeping both transistors slightly on at the zero crossing point, it entirely eliminates crossover distortion while maintaining a very respectable efficiency of around 50 to 70%. Class C amplifiers are biased so that they conduct for significantly less than 180 degrees of the input cycle, often just brief pulses. Advantage: incredible efficiency, often 80 to 90%. Disadvantage: highly nonlinear and produces massive distortion. Applications. Class C is useless for audio, but it is heavily used in radio frequency transmission like CW or FM. The distorted output pulses are fed into an LC, that is inductor capacitor tuned circuit, which acts like a flywheel to reconstruct the missing parts of the sine wave at a specific resonant frequency. From analog classes, we move to the switching classes. Modern electronics increasingly rely on switching amplifiers, which abandon the analog waveform entirely at the amplification stage. Unlike analog classes that regulate current like a valve, a Class D amplifier operates its transistors strictly as high-speed switches. They are either fully on or fully off. It converts the analog input into a high-frequency pulse width modulation signal, amplifies those digital pulses, and then uses a low pass filter to smooth the output back into an analog wave before it hits the speaker. Advantage: near perfect efficiency, often more than 90%, meaning they require almost no heatsink. They dominate modern consumer audio from smartphones to high-power public address systems. Classes E, F, G and H also exist. E and F are highly specialized switching RF amplifiers, while G and H are variations of class AB that dynamically switch power supply voltages to save energy. Here is a summary comparison between the major classes. Class A, angle of conduction 360 degrees. Linearity excellent. Typical efficiency about 25%. Primary use case: audio preamplifiers, low power stages. Class B, 180 degree conduction. Linearity poor because of crossover distortion. Efficiency typically around 78%. Primary use case rare. It has been superseded by class AB. Class AB, angle of conduction 190 degrees to 200 degrees. Linearity is good. Typical efficiency around 60%. Primary use case: traditional stereo amplifiers, linear RF amplifiers. Class C, conduction angle less than 180 degrees. Linearity is very poor, but typical efficiency is around 85%. And primary use case in RF transmitters, CW and FM. Class D, pulse width modulation, that is switching. Linearity is good. Typical efficiency around more than 90%. Primary use case: modern audio, Bluetooth speakers.